welcome to lecture 20. So, last time we saw something about the pragmatic issues, the large scale structure of the runtime system, and those structures are the basic to essentially the rest of the course. Almost all languages would follow one or the other structure with mixtures. So, let us quickly summarize those things and then we will get on to data. So, the typical structure of the runtime environment of a block structured language is something like this. There is a runtime stack, there is a heap. Usually the heap and the stack grow towards each other. So, there is the code and some certain special kinds of data are stored along with the code, and there is a current instruction pointer usually stored in a high speed register and a current environment pointer usually stored in another high speed register. Right. So, I also spoke about scope. At least static scope refers to that part of the program text in which all occurrences of an identifier refer to the same binding occurrence of the identifier. Right. So, it's a region of program text and it was illustrated with this. Such scope rules are present in most of the modern block structured languages. However, there are languages like Lisp and APL and Snowball which are dynamic, which have something known as dynamic scope. So, it is not possible to specify scope from the program text. I also spoke of extent. So, the extent or lifetime of an identifier really refers to the time during execution in which all applied occurrences of the identifier refer to the same storage location that is bound to it. So, in a statically scoped block structured language, as in the example shown before, so you have lifetimes. So, for the same identifier in an inner block, you have different lifetimes, and the different lifetimes are not necessarily related. Right. So, in most languages in the Algol 60 family, of which Pascal, Ada and so on belong, the notion of blocks is whatever we have done. We have taken the minimal subset that should define a block. Other languages have certain policies, either named procedures or functions, packages, tasks, or even unnamed blocks are blocks. And extent in such languages with the typical runtime structure that we have seen is really from the moment of entry to the block to the moment of exit from the block, and that is because the allocation is dynamic at runtime. Then we saw that there are languages like Fortran and COBOL where the scope is again delimited by a program text, and therefore, they are statically scoped. However, the extent is the duration of the execution of the entire program, and that is because languages like Fortran and COBOL perform a static allocation of storage. At compile time, every data item that occurs in a piece of code is actually allocated area. There is also something besides this. There is a common area for sharing locations between various program units, which are known to have disjoint lifetimes. So, but then it really depends upon the programmer to infer that they have disjoint lifetimes, and so they can share a common area of storage. So, it is safe only when you can actually show that whatever is in the common in different blocks they have disjoint lifetimes. Unless you can show that, there is likely to be confusion. There is likely to be an error also in your program. Right. So, you have a static allocation of storage in which most of the data is allocated immediately below the code, along with the code. and the scope of course is so therefore the normal scope rules apply. Within any program unit, all references to the data are either to the common area, which is separate, or to the locally declared data, to the local environment. Right. So the the advantages and disadvantages of doing this kind of static or dynamic allocation, pure static and pure dynamic allocation, are that with a static allocation you cannot have nestings of blocks, and you cannot have more than one activation record for the same unit, and therefore you cannot have recursion. However, since everything is all the allocation is done at compile time, the actual execution of programs is very fast. So that's one good reason why scientific programs are still written in Fortran. Another good reason of course is that there is already a large library of Fortran routines that are available, which are thoroughly tested and tried, and so there's the confidence level in those Fortran routines is very high. So if you want to actually build more scientific routines, it's a good idea to use the existing libraries. But otherwise, this fast execution is a very good reason why most scientific computation, which is very highly computation intensive and with very little I/O, is still done in Fortran, in structured versions of Fortran. The original version of Fortran was Fortran 4, which is not structured, but now you have these structured versions of Fortran, the latest of which I think is Fortran 90. They have also highly optimized the compilers so that now the execution is really fast. So you can do a certain amount of stepwise refinement with this new structured statements of Fortran 77. Fortran 90 is really a parallelized version of Fortran 77, but the whole point is that executions are fast, and scientific routines, general purpose scientific routines, are going to be developed once. And are going to be run several millions of times. So it's necessary to have fast execution even if compilation is slow. But surprisingly, Fortran compilers also compile very fast. Okay, but that's because the language is otherwise very close to the machine language and our assembly language. In the case of dynamic allocation, what it actually allows you to do is a systematic development of programs by allowing nesting. So you can actually apply a top down or a stepwise refinement method to intermix specifications and program code and derive the final code as a refinement of the intermediate steps of your program. They allow recursion, which is a very powerful specification facility, and if it's directly implementable, then it simplifies a lot of matters, because transforming recursion into iteration is not a particularly easy task. For large programs, what you would like is an automatic transformation mechanism, but that's very hard. And most of the time, the only transformations that work are very trivial sort of transformations. So as a result, there is sort of more bookkeeping at runtime in these dynamically allocated languages, in most block structured languages. And because of the allocation and deallocation that you have to do, the executions are also likely to be slower. Right, unless of course you optimize the compiler. So let's look at so the main pragmatic issues that we have to deal with in a subject like programming languages is not at the level of very deep or complex algorithms. Most of the decisions are of a policy nature. What kind of allocation strategies should we have? The actual algorithms are never very complex. The main problem is integrating all the policy decisions into a consistent framework and making something actually work, which is very hard, right? So mainly the questions are of policy decisions, and algorithms are few and far between in the traditional sense of very deep and fancy algorithms. It's really a matter of optimizing resources, optimizing uh, trade-offs between whether you want to do something at compile time, you want to do something at runtime, you want to do something dynamically at runtime, and so on, right. So the question is that what kinds of tasks should be performed at translation or compile time, what should be done at runtime, or what should be done immediately after compile time but just before runtime, you know. So there is, so then how and when is storage allocation to be done, what kinds of data require to have storage allocation done when, how can you optimize memory usage, not instantaneously but maybe over an average, or also optimize instantaneously if it's a program which requires a large amount of data and at an instantaneous moment in the execution, if it requires some, if it runs out of memory, then the program will never work. So so it's a matter of taking decisions rather than actually designing fancy algorithms, right. So and then finally, of course, what are the algorithms and what kinds of data structures which you have to use, right. So well, this is something that once you have decided on certain policies, the data structures become more or less clear, like the runtime stack, the heap, what is the relationship between the code segment and the data, what is the structure of the underlying virtual machine. If you are designing a compiler like PL0, then in which case what should be the data which contains the code, and what should be the and how should that be executed, and so on, right, which are really not very central issues. Okay. So, depending upon answers to these, you can define attributes of a data item, what kind of information. So, the answers to these questions will also determine what kinds of information you should gather at compile time, what kind of information has to be preserved at runtime in order to introduce checks, or in order to do, for example, storage allocation itself at runtime, right. So, let's look at the primitive forms of data that we already have in our language. So, the first thing is constants. So, we will, for the present, we will just assume an imperative language, very much like the while language that we have got with blocks, with unnamed blocks, and the local declarations could be either constants or variables. Complex data, we will talk about complex data, but without being too specific about it, because that is going to follow next. But right now you will find that the decisions that we require, even for something like constants, are quite a few. I mean, it's not a question of deciding, okay, we are going to have constants in this language, and then okay, now let's set about implementing them according to this semantics. Okay. So, the point is that very often you have to look at certain future, you have to look into the future to decide, you know, if you allow constants of this type, can we allow constants of another type too? Can you allow? So, for example, the first question is, okay, should constants be simple or can they be structured, right? So, now what by structured constants I mean, well, you can have arrays, records, lists, but if you allow for structured constants, then you should allow also for structures that are very large, right. So, then if structures are going to be very large, then in a compile language implementation, how are you going to assign these large structures to constants? Okay. See, so the first question is, assuming that you are going to have constants, the first question really is, are these constants going to be given values at compile time, or that is translation time, or at runtime? Okay. Now, based on that, the question is, if you have large structured constants, how are you going to assign values? Supposing you decide to have do a compile time assignment of values to the constants, then how are you going to have how are you going to do it for large constants? So, which means so the question is it so now firstly while compiling, is it really feasible to access, for example, files in a, if you're going to do it at compile time, are you really going to access and if you have large constants, then are you going to access files in the directory at compile time? I mean, are you going to do compiling and accessing various files? I mean, you might have to access enough files in order to link and load the program. You'll have sufficient hassle just trying to compile the program. Now, your compile time, especially in a language which is suitable for development, is going to be tremendously slowed if you decide to take the policy that constants have to be allocated at compile time, and you also allow large structured constants. Then you are going to also take in the values somehow from files. Now, if the constants are structured and large, and if you allow for file input, then a file typically is just a sequence, which means the file has to be formatted in a certain way, which means you may have to parse the file before you actually perform the allocation to different components of your structured constant. If it is just an array, maybe it is simple, but if it is an array of records of arrays of records, I mean, there has to be a syntax in the file itself which specifies what components go where, which means that you have a certain grammar for the data in the file, which means now you have to parse that input from the file before you actually do the allocation, before you do the assignment, right. So, the question is, are you willing to do that? So, a consequence of taking a policy like constants are going to be assigned at compile time and large structured constants are going to be allowed means that you have to be prepared for these things, right. Now, which means that the resulting slowdown in the compilation speed or translation speed, is it really acceptable? If it is a purely compiled, if it is a compiled language in which you assume that the programs are going to be run much more, the executable versions of the program are going to be run much more than the only compilations, the only repeated compilations that are required are at development time of the program, and that later it will become part of a library, then maybe a resulting slowdown in compilation speed is acceptable. But if it is going to be, for example, in a language used to learn programming, then it does not seem to make sense to, because there the number of runs is going to be much less than the number of compilations. So, what you require really are fast compilations, and these decisions may not be acceptable in such a language. So, you it's so it's such a, I mean, it's really, so it has these kinds of decisions have sort of far reaching consequences, you know, and the actual algorithms themselves are not as important as the decisions that you take in language design, in the implementation design, right. So, so then the next question is, so which this question of large structured constants is automatically raised is, when really should a constant be assigned its value, right. So, at compile time or run time. So, now supposing you assign it at compile time, okay, and supposing the constant is, you can assume for practical purposes that you have to consider also extreme cases. So, supposing that constant is embedded in a block that is very deeply nested in the program. So, then the question is, so when you this decision is that if you are going to do it at compile time, then the value of the constant itself is going to be an attribute of the constant, and it's an attribute that is going to be preserved. We have not spoken much about attributes, but in general attributes include various kinds of information that you gather at compile time. In the case of constants, it might be the value if such decisions are taken. In the case of variables, or it might, and also a type, the type of a data item is also an attribute. What is the amount of storage that is required, for example, for a record or for a double precision floating point integer? The amount of storage that is actually required, either contiguous or non-contiguous, is also an attribute that you are going to keep. What kinds of runtime checks are to be preserved, are to be kept? For example, if it's a subrange, if it's part of a subrange type or an enumerated data type, if it's a subrange type, then the bounds are also form a part of the attributes, right? So in such a case, a constant, if you decide to allocate its, if you decide to assign its value at compile time, then its value becomes an attribute of the constant, which has to be preserved through the runtime, right? On the other hand, so in general, what would happen is that if you decide to assign the values before at compile time, then the usually large structured constants are infeasible. This is in fact an excellent reason why Pascal decided to not to have large structured constants. It's a language for learning about programming, learning how to program, and so it makes sense not to have large structured constants. So arrays and records and so on are all out, right? Now supposing it's going to be allocated at runtime, then there are two possibilities: either it's allocated once before program execution begins, or it's allocated, or it's assigned each time the block in which it is declared is entered, right? So now the complexity of assigning it once before the program execution actually begins is really that, is just that at this point, if you assign it at runtime, then you can actually allow for large structured constants in some initialization procedure, to be assigned values just as you enter the block, or just before program execution, all the structured constants could be read in, right? So then but large structured constants become feasible. But supposing you do it either at compile time or once before the program execution begins, but that means, that does not necessarily mean that you have actually reached the block in which that constant has been declared, but at just before program execution begins, all the constants in all the nested blocks are assigned values, okay? But then what does this mean? This means that you are going to sweep through the entire program looking for all the constants which have to be assigned values, regardless of scope, rules, this, that, nothing. So which means that what you are going to do is that the constant cannot be part of a dynamically allocated storage, right? So which means the storage has to be away from the activation record in some safe place, so that once and only once, this is a decision you might take, especially with large structured constants, in order to save runtime, right? Once, as part of the initialization, you might just sweep through the entire program and perform an assignment of values to constants, but then you have to be careful that that storage is separate from the activation record of the individual blocks, because the activation record really signifies a dynamic allocation which has a very small extent, which does not span multiple entries into that block, right? It has an extent which is only for one particular entry and exit into the block. So then the storage has to be away, and this, for example, this is one reason why you might have some data associated with a code segment of. So in my general structure where I spoke about data under the code segment and away from the activation record, so this is one possibility. You can actually store the constants along with the code, sweep through the code and fill up all the constant data once before your actual main program execution begins. And then those constants are then available. You don't have to redo those constants. Whereas if you were to store, for example, each time the block is entered, if you have to assign a value to the constant, then again what happens is that large structured constants will have to be reinitialized, reassigned values each time the block is entered, which is going to cut down on your execution speed. Firstly, because when you are talking of large structured constants, implicitly you are assuming that they will be stored in some external files, or in some secondary form of storage, which means it's going to be much slower than memory. And it means there are going to be I/O waits, there are going to be interrupts, and if in a multiprocessor in a multiprocessed system, what it means is that this program might get swapped out, or it can become a background job, and which means the actual elapsed time will be much slower than even the lowering of this execution speed of the program. Right. So, in a standalone mode, maybe the only thing that will be visible is the slowdown because of the access to external or secondary storage. But in a job environment of a large system, the elapsed time can be much more than the slowdown in execution speed, right, mainly because the job might get swapped out for I/O. So, right. So which means that then and if it is going to be initialized each time, then one possibility is that you have storage along with the other data items in the activation record, but then you have to tag those an attribute that it is a constant and therefore it is of unchanging value is a tag that has to be carried through to runtime. It has to be an attribute of that storage location, which has to be checked at runtime to make sure that it is not updated. Okay. One benefit of having the constant stored along with the main data with the code segment is that there is a reasonable guarantee from the normal scope rules that it is not going to be altered. That value is not going to be changed, because the only things that are going to be accessed are things in the activation record. But if it is going to be stored along with other data items either in the activation record or in the heap area, then there is a possibility that you might actually by through aliasing, through various other means, you might actually change its value, right. So, unless you tag it sufficiently to ensure that it does not and put in code which prevents its implicit or explicit modification, right. So, then the next question is, should constants be assigned only literals or can they be expressions? Right. Now, but then this also depends upon whether you are going to do a compile time evaluation of that. If you allow expressions, if you allow literals, the only question that arises is again of a large structured data. I mean, so the problem reduces to whatever are the answers to the questions about large structured data, large structured constants. If you allow expressions, then what are you going to do, a compile time evaluation or are you going to do a runtime evaluation? If you are going to do a runtime evaluation, is it going to be each time the block is entered or is it going to be before execution begins? Okay. In each case, what happens is that if you are going to do a runtime evaluation, then you are always slowing down the execution of a program. If you are doing it each time the block is entered, you are slowing down the execution even more, right. Secondly, if you do it each time the block is entered, you have to ensure somehow that, I mean, then there are other questions that arise. For example, So, supposing you decide to do a compile time evaluation, then what it means is, or you do it just before execution begins. Again, it means sweeping through the entire program and doing an evaluation of all the expressions. So, one question is, should the expression consist only of previously declared constants, right? In which case it is okay, the sweep will work, but can it, and if you do a compile time evaluation, then your actual execution time is speeded up, or if you do a before execution begins, also the execution speed might be acceptable, but then, and this, if you ensure that the expression consists only of previously defined constants, then you have got reasonable guarantee that every constant is in fact a constant. But supposing you do this evaluation at runtime, at block entry time, then there is no reason why you should prevent, for example, the use of variables that are global to the block from being used, right. Since the lifetimes of different activation records are anyway different, and the constants mean different things, then the constant is not really going to be a constant. At different extents, it might have different values. So, if you allow expressions that use variables, but with the guarantee that those variables are always going to be previously declared and initialized. If you have this guarantee, for example, you could use global variables, right, variables that are global to that block. So, in which case those variables are reasonably guaranteed to have values, I mean they are not likely to be undefined, but then it means that your constant is no longer just a constant, it is a constant only for a particular lifetime. And of course, that block has several lifetimes, and so that constant might have different values at different lifetimes, right. So, and one thing of course is that the actual execution speed is going to be slowed down with each evaluation, right. So, which means that at every which means that you have a more flexible approach at the cost of execution speed, and you also live with the fact that the constant really is not constant throughout the execution of the program, but is only constant for each lifetime, and at different lifetimes it could have different values, right. So, once of course or another intermediate kind of decision that you might take is that your language might allow variable initialization, and you could intersperse constant declarations with variable declarations, and if your variable initializations are guaranteed, then a constant declaration could follow a variable declaration and use that variable initialization in an expression, right. So, but the point is that the fact that there are so many decisions to be taken at various points can what all this decision making can do is give the implementer a splitting headache, because when many of these things are not there in the language definition, I mean in the semantics, these issues are not covered, right. So, what it means is that there has to be some kind of the language design at the semantics level should ensure that the implementer can take certain decisions which might be deemed right and not take arbitrary decisions. So, that is one excellent reason. There is absolutely no semantic reason why, for example, Pascal does not allow the declaration of a variable to precede a constant. It does not allow declarations of constants and variables to be interspersed. Okay. And one excellent reason is that they just did not want to get into the headache of all these policies. They decided to stick to some consistent policy. One is that a constant is a name for a simple value expression, and it is just a name really for some expression which well, it might be very cumbersome or difficult to just type it out each time. So, you give it a value. I mean 3.14159.265 blah 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 is not a sufficient, it is not something that if you type out repeatedly in your program you will not make a mistake, it is something you will always make a mistake. So, it is a nice idea to just define a name called pi and carefully type this out and use that value throughout. Use pi as the name for that value throughout. I mean this is the, and so it avoided all these problems of trying to decide about large structured constants, what to do about them. So, one decision is that it is really, there are no large structured constants, all of them have to be variables. If they all of them have to be variables, and it is the programmer's responsibility to ensure that if he wants them to be constants, then he keeps them as constants, right. So, and what Pascal also did was that it gave one, the point is that because of this policy, actually the constants of a Pascal program are determinable at compile time. It is possible to do a compile time evaluation, but somehow they decided that it should, a constant should be assigned a value at only at runtime when the block is entered. And since there was no variable initialization in Pascal, there is no guarantee that if you allow variables in a constant expression, in an expression assigning a value to a constant, that you will actually get a meaningful result. So, they actually disallowed variable and constant declarations to be interspersed. And since there was no variable declaration, it was very clear that all constants can only use previously defined constants, right. So, a constant will actually be always constant. Only thing is they took this decision that the constant is assigned a value at runtime when the block is entered, but that is perfectly okay. But since the constant is determinable at compile time, you can make the value of the constant, you can evaluate the expression at compile time and store it as an attribute to be preserved at runtime and to be allocated storage in the activation record itself and maintain your scope rules. So, it's a simple decision which avoids, which actually sidesteps all these other policy questions that arise. So, and since it is a language for learning about programming, well, we might think that it is reasonable. Well, if you were to take some other language like Ada, which is not designed for learning about programming, but is actually meant to send satellites up and blow up nuclear installations in Iraq and so on and so forth, then what it means is then what you should allow for is that you might have large structured constants. Yeah. So, but then the point is that they still stuck to the Pascal decision of having a simple value, and but they assume that it may not be determinable at compile time. So, at each entry, maybe it might, at each lifetime the constant might actually have different value, right. So, and then what they also allowed was that you might use functions to define the values of constants, which means you are going to use variables that are already available. Since you can use functions, it clearly means that nothing is going to be actually compile time determinable unless explicitly, as in the case of pi, where there is no explicit use of variable. It is of course easy to do a scan of the program. After the scanning phase, after the parsing phase, it is possible to scan the program to find out about dependencies for each constants, for each of the constants, and actually clearly demarcate which constants are evaluatable at compile time, which constants are evaluatable at only at execution time, and take a decision on the fly and make sure that you fill up those decisions at runtime during block entry time. So, and they also allowed structured constants like arrays, records to be permitted. After all, remember that maybe a Pershing missile requires to know the exact longitude, latitude, the altitude of a nuclear installation in Iraq, right. So, and so you require large structured constants. Okay. So now let us get on to variables. So in the case of variables, actually the problems are not so severe. There are a few default decisions that you have to take, but more or less things are, the only other decisions are really that of storage. Should initialization be allowed? Should initialization be mandatory? But then initialization being mandatory is something that not everybody likes, because the whole idea of a variable is that it provides you a lot of flexibility. So the only other question is, should initialization be allowed? One possibility which has is that in, for example, the language Pascal does not allow for any initialization at all. The syntax itself throws out the notion of an initialization. Languages like Ada actually provide a small, allow you to provide a small set of initial values. So even though it might be a large structured array, for example, what you could do is, so you could have a declaration of this form. Yeah. So let me call this IR. Array maybe 1 to 10,000 of real, yeah, and you could have something like this, an initialization which actually looks something like this. 1 to 5,000 have been assigned the value 0.0, and 5,001 to 10,000 are, let us say, allocated the value 1.0. I mean, this is approximately how the syntax would look, syntax of an initializer. So large structured values like large arrays, if you provide a small set of initial values, when you could actually write it out, enumerate in such a fashion. But if all the 10,000 values are going to be different, then you have a severe problem, right? They do not answer this question as to what they are going to do in such a case. I mean, after all, why should I be restricted to 2 or 3? I mean, why can't I write 10,000 different clauses? The other question is, do you think a programmer is actually going to write 10,000 different clauses? He will take the easy way out and just write to 1 or 2 values, that is it. And so what he will do is, he will read it, or read the rest of the values from file and something, or he will do something, but is not likely to use that initialization unless he is absolutely sure that there are only a few initial values possible, right. And so the question is not, so the question of whether it is going to be mandatory is useless question to ask, because in the case of large structured variables, and variables you can't prevent large structured variables, I mean they have to be there, right. So that is not a decision that is open to you. If you want your programming language to be actually used by people, then you better allow for large structured variables. So but you can, so you just have something that is not mandatory, but it allows for it provides for a small set of initial values, which, what is the size of this small set of initial values is something that might be implementation dependent. In the case of languages like Fortran, for example, there is an explicit data statement which allows for an initialization. Again, as in Fortran, there are no, I mean it is not mandatory, and of course everything is initialized by default, even if you did not provide an explicit initialization, whether you like it or not. So whatever is not initialized by the data statement anyway has a default initialization in Fortran, right. But essentially Now, if you look at, if you get back to our structure, our typical structure, and then actually you would see that if you get back to this typical structure, then actually you would see that if you are just looking for possibilities of keeping of allocating storage to variables, then you could allocate them either here or here or here. There is absolutely no reason why you can't allocate them in any of these three places, if this is going to be your typical structure. And in fact, we do have, of course, there have to be good reasons why you want to allocate something here or here, if your default allocation is going to be in the runtime stack. Okay. Excuse me. So, as far as the heap is concerned, it does not really matter. The heap is used for a dynamically allocated variable. So, the heap is really going to be a heap, it is going to be like a garbage heap. Okay. So, which means that for explicit allocation and deallocation of variables, you can use the heap, and that is the policy most languages follow. But what about here? So, there are these, so the heap space is mostly used by all languages which allow for a heap space, and where there is a dynamic or explicit allocation and deallocation done by the user of the language. Yeah. So, the scope of course of a variable is still the block containing the declaration of that variable that has to be dynamically allocated, and the extent of that variable is also determined by the programmer. So, therefore, the extent is from the time the program explicitly creates that data object to the time the program explicitly deletes it from the heap, right. So, there is an explicit creation and deletion. I mean this, so for example, languages like Pascal has this new and dispose, which are explicit creation and explicit deletion commands. Other languages like PL1 and so on have this thing called automatic. I mean in those days PL1, since it followed Fortran immediately, they had to clearly specify what is automatic, what is controlled, what is static. I mean the static was supposed to be Fortran, the automatic was supposed to be what is normally a variable in a block structured language, and the controlled was explicit programmer creation and deletion, right. The other possibility is to actually use the own variables of Algol 60, right. So, as I said last time, the problem that the Algol 60 designers felt was that how are you going to use random numbers unless you have a procedure which is somehow history sensitive. It really depends on how many times it has been called before. So, there has to be some variable, the seed of a random number generator should be changing every time, and normally what you would do is you would take the last random number generated as the seed for the next invocation. So, which means that in such a procedure you require a seed whose value should be retained between different lifetimes of that procedure, right. So, most languages actually allow for this version of own variables, and normally these own variables, since their values have to be preserved between two different lifetimes of that block, these own variables are stored in the data area under the code segment. I mean that would be the normal place to store them, so that they do not get washed out with when you do block exits, right. And note that heap space is still accessible only through the runtime stack. So, if the runtime stack, if your activation record gets washed out on block exit, then you can't store the own variable in the heap because because the pointer to it has been lost. It is as simple as that. So, the third space is that reserved space allocated to each block in which history sensitive variables may be stored. So, they have this reserved word called own for a variable, which for example in C and PL1 they call static, which retains its value between successive invocations, and you can use that. The only problem with these own variables is that if your language does not make variable initialization mandatory, then there may not be any initialization, which means each time you call this procedure which has an own variable, you have to introduce code in your calling procedure to check whether it is the first time that procedure has been called or not. And if it is the first time, then you have to provide maybe an initialization value for the own variable. If it is not the first time, then you just call it. I mean, that's it. So what it means is that you require to introduce for every call to that procedure which contains a known variable. If your language does not allow initializations and declarations, what it means is that you have to write a cumbersome piece of code to ensure that, to find out whether this is the first time you are calling that procedure or not. Yeah. So normally this allocation is with the code with the code segment. If in languages with default initializations, then there is no problem of checking whether it is the first time or not, and most languages which allow it actually allow for explicit or default initializations. Yeah. So we might finally classify variables in this form. So you have variables which are automatic in the sense that they are created at block entry, they are deleted on block exit, and the area where they are stored is a runtime stack. You have static variables which are created when you enter the program, but may not be initialized depending on the other features of the language. Okay. They are deleted when you exit the entire program. So they have an extent spanning the entire execution of the program, and the area is usually the code segment area. And there are control variables which are explicitly programmer controlled, which are created by an explicit programmer command, which are deleted by an explicit programmer command, and they have a lifetime. They are stored usually in the heap, and they have a lifetime between their creation and their deletion. Yeah. Okay, we will continue on data next time.